Hello, everybody. Very glad to be able to welcome you to the latest edition of the Australian Geothermal Association webinar series. My name is Mark Ballesteros. I'm the president of the organization, and today we are going to be hearing about designing geothermal borefields, practical insights into why and how from Wouter Peere, and which will be joining us in just a moment. And I'll just do a little editorializing here first. The AGA is the peak body for Australia's geothermal sector. So we provide a forum for individuals, organizations, and anybody interested in geothermal energy information, discussion, networking, support, and advocacy. We are an affiliate of the International Geothermal Association, and we're born to promote and encourage the science, technology, and development of geothermal. You can see our website address there. I encourage you to go check that out. I'd like to acknowledge our corporate members who you can see listed on the right-hand side of your screen. We appreciate their support. I also want to put in a big plug for an event we have coming up on the 8th of September. So that's it's less than 2 months away now, a global geothermal showcase 2025. This is going to be a live event at the Shine Dome in Canberra, ACT, but will also be available to attend live online. So if you can't make it to Canberra, you can still attend and hear the stuff. So this is basically stirred by the fact that we're going to have a visit to Australia from Marit Brommer, who is the CEO of the International Geothermal Association. So we're very excited to have Marit coming, and she's going to be doing several events, but this one is going to be the first and arguably the biggest. The intention here is to be able to bring any and everybody that's interested in geothermal in Australia up to date on some of the latest technology developments. There have been some very exciting things that have been happening in the last couple of years that are really changing the landscape as far as the potential for geothermal, both technically and commercially. And this event is going to be designed to have be addressed from Marit to tell us where things sit in the world in general. And we've got a number of very exciting speakers that are going to be presenting both live, and some will be doing it virtually, on updates on the new technology developments. That'll be including EGS, AGS, the direct use ground source heat pumps, geothermal on a global scale, and how all that will impact on Australia in the future. So I encourage you to note the date and put it in your calendar, 8th of September. That's a Monday. If you're able to make it to Canberra, please join us at the Shine Dome. Otherwise, you can log in live. And I think we'll probably have that available subsequently as a recording as well. There'll be more information coming out very shortly on that in the next week or so. So you might check our LinkedIn page for further announcements and details for registration and or the website. But yeah, keep your eye peeled. That will be a big event for us. I also wanted to let folks know that the latest new release of the geothermal titles map is set to be posted online here in the next few days. So if you're interested in that, you can check the website, and that will be available as a PDF file like what you're seeing on your screen there to anybody. And if you're a member, you're able to actually download a QGIS project that's got all the metadata behind that as well. And also mention just briefly that video recordings and slides from the past webinar presentations are available for members on via the website and our AGA YouTube channel. There's a link there. So again, I'll suggest you go check out our website, and you'll be able to find that link there. Okay, so without further ado, I will introduce our speaker. So Wouter Peere graduated in 2020 as a mechanical engineer from the Catholic University in Leuven in Belgium. His thesis topic was hybrid geothermal design. He spent 3 years doing postdoc research at the university in close collaboration with Boyden's Engineering, at which point he started his own engineering firm, Enead, in 2023. So Enead is the main developer and distributor of GHE Tool, which is a cloud-based borehole sizing tool for both small and complex geothermal systems. And Wouter's going to be telling us about how one can apply that to designing systems and making things more efficient and effective. So without further ado, over to you, Wouter.
Thank you, Mark, for the introduction. Thank you all for joining us. It's a pleasure to speak to the other side of the world, where it's now afternoon towards evening, and it's here not too early a morning, but still early. I will be indeed talking about the design of shallow geothermal borefields. I will give you some theoretical insights in how the system behaves, but I also want to give you some practical information. How can you design such a system, and why should you care? Now, just as a little bit of context, we are all here because we love or believe in geothermal energy. But geothermal energy is a very broad term. There's quite a lot that falls under it. So just to give you a little bit of context, we have the deep geothermal systems, the systems that go over a kilometer deep. This is what we call the direct use systems, where we can get really hot water, even steam, out of the ground for electricity production, or for the heating of baths as a replacement of gas. Really interesting. We're not going to cover that today. We're going to talk about something which is called the ground source heating and cooling, with ground source heat pumps, which have way lower temperatures. And instead of using the ground as a source of heat, we're actually going to use the ground as a heat battery. So we can cool with the ground, we can heat with the ground, and we store this energy in our geothermal system. And more specifically, we will be talking about closed loop geothermal systems, so boreholes up to 100, 150 meters deep. Now, this type of technology, it's very flexible. It can be used for residential houses, it can be used for commercial buildings, office buildings. So it's basically, you drill a hole 150 millimeters in diameter, or sometimes smaller, 100 meters deep. You put in a heat exchanger, you connect everything to your building, and by letting the fluid circulating through these pipes, you can actually exchange heat with the underground. So it's a shallow system, it's a heat battery, and it's called, or I will call it, borefields or beta systems. It's also sometimes called. Now, this technology is not new. The first patent was in Germany in the 70s. And since then, ground source heat pumps have been increasing in popularity. These are some figures from the latest market report in Europe. There are over 2.4 million ground source heat pumps in Europe, and most of them are connected to smaller borefields or bigger ones. And last year alone, there were over 100,000 units sold, specifically or most often in Sweden and the Netherlands. Now, I will not talk too much about the situation in Europe, but it's a really common technology, and the reason why it's that much used in Sweden and the Netherlands is because they mastered the skill of drilling, and that makes the borefield also really economical. And I want to say that because it's not a technical issue. In Sweden, it's mostly rock. In the Netherlands, it's mostly sand. So from a technical perspective, there is no difficulty in getting the price down. It's getting the experience, it's getting the belief from the market, and then the price of the drilling will automatically go down. So this is the situation in Europe. There is also some geothermal in Australia. I got this information from the census that the Australian Geothermal Association did a couple of years ago, where you see that most geothermal installations are at the southern part of Australia. And if we take a look at the distribution, because that's for all type of geothermal systems, we see that there are quite a lot of direct use systems where there is actually hot water, 80 degrees, coming from the ground that we can use to directly heat our buildings or springs. For example, we have the Great Artesian Basin in Australia with some hot water baths. That's also geothermal energy there. But here to the left, we have our ground source heat pumps for both heating and cooling. In 2018, it was a rather modest part, but it was expected to increase towards 2025. So I'm really curious to hear next year whether or not we reach that target. Now to give you some case studies, just to show that it's used borefields in Australia. The people over at Geothernal were kind enough to send me some of their references. So they've been installing and designing geothermal systems for since the end of the last century. And these are some of the bigger projects. So it's a research center, the Geoscience Australia, but also a swimming pool in Thredbo, which is not that easy typically to heat with geothermal because there's quite a lot of heating but also cooling. So it's a really interesting design to also do that with the geothermal system. And the Parliament of Victoria is also recently upgraded, let's say, to be heated and cooled with a ground source heat pump and 56 boreholes of 100 meters. So these are for the bigger projects, but there are also case studies for smaller residential projects. So we have here a very interesting looking house in Sydney. It was actually called by an architect a piece of sculpture to be lived in. So it won quite a lot of awards, and it's also heated with a ground source heat pump and a couple of boreholes. And then we also have a residential project with apartments, where each apartment has its own small ground source heat pump connected to a geothermal borehole. So also in these collective housing, geothermal systems are an option. So both in Europe and in Australia, there are quite some example projects. Now let's talk then a little bit about the case for borefields, and because it's not because there have been examples that it's a good solution, because most people associate geothermal energy with a high investment cost. Now I want to say that it's probably higher because it really depends on how you design your systems, but we will come back to that. So probably it's a higher investment cost, but the efficiency is also better. So a ground source heat pump has a 25 to 50% higher efficiency than an air source heat pump. Now the percentage, of course, depends whether you're in a colder or a hotter region, but overall the performance will be better. And this has an impact on the running cost, of course, because if we take a typical house with a 50 megawatt hours per year of cooling and a 9 megawatt hours per year in heating, we know that the electricity cost for that will be around 2,500 Australian dollars for each year. Now, if we take this 25 to 50% off of that, we can save 600 to more than 1,000 Australian dollars a year, which over 20 years, which is typically the lifetime of a ground source heat pump, can go up to more than $20,000. So if we take that into account, there is a payback period for this more expensive project, and it will save you quite a lot of money in the end. But next to the economic reasons, there are also more qualitative reasons why geothermal borefields could be an interesting solution for your project. So there is no noise pollution because we have no outside unit, no fence spinning. And that's important more and more in cities. It's not nice that your neighbor has a fence spinning 24/7 to cool his building. With ground source heat pumps, that's not the case. So that's a nice benefit. Also, in some regions of Australia, the coastal regions, the lifetime of air source heat pumps are not that great. The sea has sea salt. The sea salt comes into the air, and it's a really aggressive environment for the air source heat pump to live in, to be in. it corrodes its heat exchanger, etc. So the lifetime of air source heat heat pumps are not that great in some areas. We have the issue of security of supply. So if it's really, really cold outside, an air source heat pump might struggle to heat your building because it can't get enough heat out of the environment. Now, this is not a problem with the ground source heat pump because the ground temperature will always be hot enough. It will always be warmer than the environmental temperature in winter. So that also is a benefit for the geothermal systems. And lastly, which is more subjective, of course, it's associated with more high-end buildings. Ground source heat pumps are seen as being the premium option, the most robust, the most environmentally friendly building. So it's typically installed now for the more high-end building, the prestige projects, etc. I also mentioned there the aesthetics. We have no outside units, so it's just a little bit nicer, let's say. But of course, that's subjective. So is there a case for geothermal borefields in Australia? Yes, there is. But it's only when it's designed accurately. So this means no oversizing, so it becomes economically feasible, and also no undersizing because we want our system to keep working. So that's why design is actually important, and it's not that trivial to design a borefield. And this brings us to the main agenda of today. So I will give you a crash course in borefield physics. We will not talk about mathematics, but I just want to give you insights in how these systems behave so that you know as a designer, as an engineer, as a driller, as an installer, how you can change your system in order to come up with an affordable geothermal source. I will talk about where you can find required information, where you can find sources, and I will also briefly show you how easy it is to actually simulate such a system and start doing your own design. Now, when we talk about the design of geothermal borefields, we're talking about fluid temperatures. So we're circulating a fluid to the borefield, and we want this fluid to stay within certain limits. In other countries, there is legislation for that. In Australia, there is not yet a legislation. So we need to rely on good engineering practices, let's say. For the minimum temperature, we typically want something around 2 degrees Celsius because we do not want the ground to be freeze down. That's not good for the system performance, but also not good for the ecological context for the macrobiological life in the ground. The maximum temperature, it depends. I mentioned here free cooling. Now, free cooling is a cooling solution where you don't need your heat pump. So the ground is cold enough, so you can just circulate the water through your building and into the ground, and you don't need the heat pump. This is typically used in Europe, so we design our borefields to be typically below 18 degrees Celsius. Now, with the cooling demand of Australia, that's almost never a case. So we use a heat pump for active cooling here, and we want to limit our temperatures to 40 degrees into the ground. Above that, our system will also be not that efficient. Minerals will start to dissolve, and we will again get some ecological uncertainties there. So let us take a closer look at the graph below then. I show you another one, which is a little bit more clear. And here you can see 3 lines. And we see a time horizon of 20 years, temperature profile, and 3 temperatures. And of course, we're a geothermal system, so what's important is the temperature of the ground. And that's illustrated by the black line. That's the borehole wall temperature. That's the temperature at the interface, basically at the interface of our heat exchanger. And as you can see, it varies over the seasons. It heats up in summer, it cools down in winter. And there is also, over the years, a certain drift. So in this case, it heats up year after year a little bit. And then we have a blue and a red line, and these are for the temperatures during heating and cooling. So if we're cooling our building, we're injecting heat into the ground. So we pump a temperature which is higher than the ground and the borehole wall. into the ground. And with cooling, with heating, it's the other way around. There we pump a fluid which is colder than the ground into the bore field in order to extract the heat. And we want to stay between these dotted lines. So in case we cross it, we need to drill extra in order to make sure that we stay within these limits. So it's really important to get a feeling on, okay, what determines these profiles and what determines the drift on the long term, but also what determines this delta T, because we have the ground temperature, that's a given, we cannot change that. But if we can lower the difference between our fluids and our borehole wall temperature, then we can actually make the bore field as small as possible, which makes it more economically feasible. So talking about the thermal behavior, we can make a distinction between the short and the long term. So on the short term, in a matter of hours, the ground temperature can be assumed to be constant. If we cool now our building with 10 kilowatts, we inject 10 kilowatts into the ground will not heat up until after a couple of days. So that takes quite a lot of time before the ground really starts to change. So on the short term, we can assume the ground temperature is constant, but along the long term, months, years, the seasonal and yearly variation, there the ground temperature varies. And that's what we call the long-term effect. Now for the short term, this is the only equation I will show you. We can say that the fluid temperatures we have in heating and cooling is equal to the borehole wall temperature from which we start, plus or minus a certain delta T. Now we have here our borehole wall, we have our two pipes with an average temperature, and then we have here a specific power exchange with the ground. So if we have, let's say, 10 kilowatts of heat injection into the ground, we have 200 meters of borehole, then we have 50 watts per meter of power that we exchange. And this goes through an effective borehole thermal resistance. Now, if we take a look at the electricity world, we're all familiar with the law of Ohm, which states that the voltage across a certain component, electrical component, is equal to the current through that component multiplied by its resistance. Well, the same can be said about heat transfer. So if we have a certain thermal component, a physical object, we put a heat power through it, the heat flow through it. If we multiply it by the resistance of the system, we get the delta T across this component. And the resistance in a geothermal world or in a borefield world is called the effective borehole thermal resistance. Now, this is a really important aspect when it comes to the design. And what it is, it's basically the resistance the heat feels when it wants to travel from the fluid to the borehole wall. So if we start in the fluid, we first need to pass our heat from the fluid to the pipe, which is a convective heat transfer from a fluid to a solid. Then the heat has to pass through the pipe. And then once it's through the pipe, it also has to pass through the ground, so through a filling material. And it's these three resistances together that actually make up the borehole effective thermal resistance. And the good thing is that as a designer, as a driller, we have an effect on these parameters. So first of all, the pipe resistance, the middle one, is grayed out because we're not going to develop a new type of plastic. So we assume that that's a given. But what we can change is the fluid regime. So if your fluid is flowing slowly, it's called a laminar state. So if you open your water tap at home, you will see that if you do it slowly, that the water is well behaved. It comes straight down. And this is not very good for heat transfer because the parts that are in the middle of the fluids, they will never touch the wall. So it's hard to give away the heat. And that's why we want to go to turbulent systems where we increase the flow rate so that the water starts tumbling and that every particle touches the wall one moment or another, and it's easier to give away the heat. So we want to work with a turbulent flow regime. For the pipe to grout resistance, of course, we want the pipes to be as close to the borehole wall as possible. How do we do that? Well, we want to try to drill as small as possible. We also want a grout, so our filling material with a very good conductivity, so it's really easy to give away the heat. A double U-tube, so putting 2 heat exchangers instead of 1 into the borehole is also beneficial because you have more heat exchange area. And all these parameters affect this borehole resistance. Now, if we look back at our figure, we have a fluid temperature. On the short term, the borehole temperature is assumed to be constant. We have our resistance, but this is multiplied by the power per meter. So what this learns us is that on the short term, our borehole resistance is important, but also how much meter borehole is there. Because if we have 10 kilowatts for 200 meters or for 300 meters borehole, this actually decreases this parameter by 33%. So on the short term, it's important how much meter borehole you have. Just to summarize, the effective borehole resistance is typically between the 0.05 and 0.25 meter Kelvin per watt. And it's a power problem. It's because we assume that the ground is more or less constant. It has to do with how much power we want to exchange at this very instant. And the important parameters are the ground, thermal conductivity, fluid regime, where the pipes are in the borehole, and also your total borehole length. So that's for the short term. That's this delta T between the wall and the fluids. Now we also have our long-term behavior. Because, of course, if we are injecting heat into the ground, which we don't take out, the ground will heat up year after year. And if we have a bore field, it's quite a complicated problem because all the boreholes, they interact with each other under the ground, they feel each other. And we also interact with the infinite grounds. And that's what we can describe by using G functions. It's a concept developed in 1987 by Eskilsson. Scandinavia. And what he said is, well, okay, if we have a certain bore field and we inject a constant power, how will it react? And that's basically what you see here. So initially, the borehole will heat up quite fast, and that's because on a short time scale, a couple of days, the heat is all centered around the borehole. And it's only after months and years that the circle of influence increases and the heats get dissipated away. And the more you do that, the longer it takes to heat up the borehole. And that's why the slope decreases here. And this is also something you as a designer have an influence on. Because if you place your boreholes close to each other, you will see that they have the same curve, but the blue line is where the boreholes are closer to each other than the green line. So the green line can better cope with the imbalance between heating and cooling because since the boreholes are further away, it's easier to dissipate the heat to the environment. The other thing is the configuration. If you place your boreholes in a grid versus you place them on a line, in the line it's also easier to give away heat. You have simply more ground to interact with, so that's also beneficial for systems which have more cooling than heating demands. So to summarize this long-term behavior, then it's an energy problem. It has nothing to do with power. Power is instantaneous, but it has to do with how much do you heat and cool your system, your ground, over the years. And important parameters are the borehole spacing, the configuration, but also your ground conductivity. If you have a good conducting soil or a bad conducting soil, that also affects how your system will behave on the long term, of course. So this was just very briefly what's behind these graphs and which parameters are important. Now I want to go over some print screens of our software to show you what information do you need in order to make such a simulation, such a temperature profile. So we have some general simulation parameters. We need a minimum and a maximum fluid temperature, a simulation period, and also in which month we start the simulation. Because if you start in winter or you start in summer, that will give you another behavior. Next, since we're working with a geothermal system, we need information for the grounds. Now in Australia, it's typically sandstone and rock. So it's between 2 and 3 watts per meter Kelvin, which is really good conducting. So that's a good thing. You can also measure it in situ. And we need information for the ground temperature. Now there is a free website online, Project Innerspace, and you can also measure it. So just a brief print screen of this project. You can go to the URL, it's free. You can select the location, and there you see, well, this is our ground surface temperature. It's 19 degrees on average in Perth, and we know that the ground gets warmer by 18 degrees Celsius per kilometer. We go deeper. So that's actually the information you need for the software to actually simulate the ground temperature. If you really want to be sure of your specific location, you can also do a thermal response test. Therefore, you drill a borehole, you connect a measurement device to it, and it's going to inject heat into the ground, and it's going to measure the temperature that comes out of it. And by doing so, we can measure the initial ground temperature, we can measure the conductivity at this specific location, and we can also measure the borehole thermal resistance. Now there is an asterisk behind this, and that's because you need to make sure that you measure this under the same conditions as you're going to use your system later. If your flow rate is not the same, if you use antifreeze in your system and not in the measurement, it can give you wrong results for the resistance. So just keep that in mind. If you do a TRT test and you want to use the borehole thermal resistance, make sure it's done with the right conditions. So that's for the ground parameters. Next, we need to design our borefield. So we can do that with quite a lot of options. Here I just put 3 boreholes next to each other of 100 meters deep. Once we have selected our design, we need to select what's going into the system. So in this case, I used 2 DN40 probes with a grout of 1.5 meters Kelvin, watt per meter Kelvin, which is a rather good grout. We can go up to 2 or even 2.5 for very extreme cases. And I typically select the pipes to be somewhere in the middle, which is something I can, not I can promise, but which seems reasonable. Now, something I want to note about these heat exchangers, there are also innovations here. So we have the turbo collector from Wouter, which is a pipe with fins in it in order to enhance the heat transfer, to make it sooner turbulent, which also, again, decreases the amount of boreholes you need and makes your system more economically feasible. The one on the right can be interesting for the geothermal market in Australia. It's Separatus. It's a 2-year-old innovation from Switzerland. And what they did is, instead of using a traditional U-tube, they took a TN50 pipe, they installed a membrane in it, and it's just one pipe that now goes down. So it's way easier to install. And you can also drill with smaller drilling diameters. I know that Coloric also already gave a presentation here. They have a drilling rig which is capable of drilling small boreholes, which has the advantage of drilling faster. You need less grouting. You can install everything a little bit faster, and that makes your system also more economically feasible. So the Separatus system can be interesting for your market. Now, once we've selected the pipe, we need some information for the fluids. Typically in Australia, it's monoethylene glycol or water. Since you're mostly cooling your buildings, you can work with water, which is really good for the heat transfer. And then lastly, you need some information about the load of your building. So the heat pump efficiency data, which is for a ground source heat pump, really good, as COPs of 6 are easily to be reached in Australia. And then you have your yearly energy demand. So you have your peak power in heating and in cooling, and your yearly energy demand as well. Now, where do you get that? That, of course, depends quite a lot on the insulation degree of your building. Do you have a passive house or is it a renovation? Do you have quite a lot of glazing or not? Is it commercial or residential, and where is it in Australia? Now, some rule of thumbs, residential buildings typically tend to have 40 to 50 watts per square meter of heating, 70 to 80 watts of square meter of cooling. These numbers also came from the guys over at GeoExchange. For the yearly energy demand, we have some rule of thumbs, but it depends on the region you are in Australia. You also have heating degree days and cooling degree days, and there is also a website. So this is a map from the government where you can actually see that the south of Australia, as you all know, it requires less cooling, and when you go to the north, it has more cooling degrees. And for heating, it's the other way around. So if you think about geothermal borefields as it's a heat battery, then this region in the south, it's really interesting because in cooling, it has around 500 cooling degrees days, and in heating, it's also the same. So you're really using the ground as a battery. The higher you go up, the more you will have an imbalance between heating and cooling, the more your ground will heat up over the years, and the more you should pay attention to the correct design of your system. I also briefly want to show you this website. So with renewables.ninja, you can select a location, you can fill in some building parameters, and it will give you back an estimated heating and cooling demand for your building. So that was just some brief explanation. Now, to make it really practical, I wanted to share my screen and really show you how the system can be designed in practice. So this is a building in Perth, certain amount of heating and cooling, and domestic hot water consumption. So I will hop over to GHG tool, show you how you do a design in practice, and then we'll wrap up this presentation. So let me end this. Perfect. So this is just a project in GHG tool. I entered the simulation settings, our ground parameters, as I showed you the conductivity between 2 and 3, the ground temperature, as was the case in Perth. I say, well, let's start with 2 boreholes 6 meters apart. I will use a double DN40, PN16 with our thermal conductivity. We use 0% of antifreeze. It does not matter which antifreeze because there is 0%. And for our thermal demand, we said we have 4,000 kilowatt hours per year in domestic hot water, and we have here our cooling and heating demand. And if we then go to the results, we see that we have a maximum temperature of 42.65 degrees. So we are a little bit over our threshold, and for heating there is absolutely no problem. So our heat pump is really working efficiently here. Now, to show you how you go about such a design, what we can do is we can duplicate the scenario, and I will call this 3 boreholes. Because we cross our temperature limits, so we can say, well, okay, let's now simulate with 3 boreholes. And then you will immediately see how the system reacts. So if we have 3 boreholes, we see that our maximum average fluid temperature is now only 35 degrees, where it was 43 almost before. So just as the last step to show you this, you can see, well, now it's oversized. And because that's a little bit of danger, you say, well, let's not do it, it's 3. But now our system is oversized because we can go up to 40 degrees. So what we can do is we can actually ask the software, well, calculate now my required depths. How deep should I drill in order to stay within these temperature limits to really get an economically ideal solution? And here you see that we need 3 boreholes of 73 meters deep. And then we reach our limits beautifully. So here we have a system which we know will work. And we have also a system that's economically optimized. We have the exact amount of borehole meters to heat and cool our dome. Now, let me wrap this up. So, if you think geothermal engineering and the design is interesting, we have also a YouTube channel with more than 10 hours of free videos on ground source heat pump, the design of borefields, the physics, whatever you want. We also have a knowledge base. We write weekly articles on everything geothermal, ground source heat pumps, the physics, the separator system, you can see here, TRT tests. So if you need any background information, any literature, there's over 200 pages of text there, so you can find everything you want to know. And with this, I want to conclude this presentation. Just want to say, if you want to try out the software, feel free to schedule a demo. We go over a project of yours. I'll show you around the tool so you can use it yourself if you want. And I welcome any questions you as the audience may have. Thank you.
Excellent. Thank you very much, Wouter. That was very interesting. Looks like that software can sort out a bunch of problems. As far as the questions go, what I'm proposing to do is we'll turn on people's mics and they can ask them themselves, but perhaps you could raise your hand in the chat room or Q&A or something if you have a question, and we can just regulate a little bit so we don't get everybody at once, but that's probably easier to ask the questions directly. So while folks are getting organized there, Wouter, I've got a question for you. Do most of the systems designed in Europe use antifreeze, and how much does that affect the thermal response of the system?
Now, currently the software is mostly used in Europe, and since our climate is typically colder, we almost always use antifreeze. In Belgium, it's typically monopropylene glycol because it's non-toxic, but it's actually very bad for the heat transfer. It makes the fluid more viscous, and the resistance, the borehole resistance, it can actually be 2 times as high due to that. There is a tendency in Europe to more water-based systems, like you have here in Australia, which are way more performance, way better heat pump performance, way lower pump energy consumption, better designs. But yeah, it takes quite a lot of effort to change a whole market into that philosophy. But it makes a difference, yeah, quite a lot.
And following on from that, is there a lot of environmental regulation that I'm imagining if you developed a leak or something like that in the borefield, that you'd get potential environmental issues? How is that handled to prevent that from happening, or be aware of it if it does?
Well, typically the leaks do not occur in the vertical part of the system. These are pressure tested. It's mostly in the horizontal connections where the risk is. But in Europe, most countries have a legislation on what type of antifreeze you can use. So you can only use environmentally friendly alternatives. So when it leaks, it does not harm the groundwater, etc. In some regions where there is groundwater, it's prohibited to drill certain systems in order to make sure that there is no contamination of it. So there is quite a lot of legislation, but it again depends on the country to country. Yeah.
Okay, thank you. Okay, looks like you have convinced everybody else so thoroughly. I don't see any other questions coming up here. There we go. Soren, go ahead.
Yeah, thank you. Very good presentation, Wouter. And I'm not a a person dimensioning geothermal wells, but and I couldn't pick it up quick enough. But I see in some areas they also start making you can say geothermal wells in a pyramid shape from a, you can say, small surface area, and then drill a pyramid and have a number of holes there. And I was not quick enough to see all the options that you have in your software, but is that something that can be picked for a simulation as well in your software?
Yeah, just to clarify that for the other persons who might not know what we're talking about, in the figures I showed you, we assume that we drill straight down. Now, if you have limited area, what you can do is you can position your drill rig and you can drill under an angle, so you can in densely populated areas. That's an option. Yes, you can simulate it, and it's actually interesting because your collector cost will be lower because the boreholes are closer together. But since you're diverging away when you go deeper, the average distance between the boreholes is also very, very big. So it's also good for the long-term effects. So yeah, that can be simulated. It's quite often done in France. It's done in Sweden. There are quite a lot of angled system in Brussels. They're also now starting to do that. So it can be interesting. Since in Australia there is quite a lot of rock and hard sediment, perhaps that's also interesting to try out in your market for specific projects. Yeah, thank you for the question.
Well, that was a very interesting question, so I'm going to ask a follow-up to that. Does your software require you to specify the different borehole angles and design of the borehole field, or is that one of the options that you can select so that it can basically decide an optimized way to drill the wells to get the best thermal performance and minimize cost?
Now, what it can do is it can calculate the depth for you. In a couple of weeks, the method is now in development in Germany, the university in Aachen. We will also be able to position the boreholes optimally. So now it's more from an engineering point of view where we say, okay, we have place to drill here and here and here. How deep should we drill in order to be able to fulfill the building demands? So yeah, you can simulate it that way.
Okay, thank you. Graham, go ahead.
Thank you, Mark. Thank you, Wouter. Your software does a very precise calculation of the required length of drilling to produce a certain amount of heating and cooling. How sensitive is that to the assumed thermal conductivity of the ground?
Yeah, it depends a little bit. It depends, of course, on the size of your system. So the thermal conductivity of the ground is important for the long-term behavior, right? It depends. If you have a building which has way more cooling than heating, it will determine how the bore field reacts on the long term. So this is especially important for bigger projects when there are quite a lot of boreholes interacting to each other, and this effect is way stronger visible than for residential ones. So that's why for bigger projects, it typically makes sense to do a TRT measurement, to measure it in situ, and to know whether it's 2.3 or 2.5, let's say. Because for larger projects, that can actually matter a couple of boreholes.
Okay, so you drill a first hole to like 100 meters or something and do the in situ test, and then calculate what you still need to drill. Okay.
That's typically what's done in Europe. So you design, you make an estimate, a budget estimate, you do a test, and then you update the design afterwards.
You update it. Okay, thank you.
I also saw a question popping up in the chat from Andrew.
Yes.
The software does calculate pumping costs, hydraulic design as well. This is not a webinar about the software, but yeah, it can do that. And if you're interested, please feel free to email me afterwards, and I can show you. But yeah, hydraulic design is often overlooked when designing geothermal systems, but it's an important aspect as well. Yeah.
Thanks very much.
You're welcome.
Okay, excellent. Any other questions? Okay. Wouter Peere, thank you very much for that presentation. Very interesting, and thanks for getting up early for us. And I'm going to just flash up the my little advertisement for the Global Geothermal Showcase again, as we say thank you once again for participating and sharing that knowledge. As I mentioned before, this should be available on our website and our YouTube soon. So yeah, stay tuned. And any other questions for Wouter, pass them on through. Can give you his details, and you can play with the software yourself, and or yeah, follow up with anything else that may come up. So without further ado, thank you once again, Wouter, for sharing that with us, and we'll look forward to follow-ups from here, and hopefully for lots of opportunities to make that system work as our number of installations in Australia goes up.
Thank you. Thank you for your time, and have a nice evening or afternoon.
Okay, thanks very much. Bye now.
Bye.
Thank you all for participating.
Thank
Okay.
you.